talking about the individual molecules for up to this point. But now we're going to learn about how molecules can stick together. So the formula unit of a molecular compound is a molecule. But then to have a molecular compound, you have lots of molecules that are connected together somehow. So we're going to talk about those connections today. Okay? So two of them are called van der Waals forces. They're named after a Dutch chemist named Johannes van der Waal. Where these are actually the two weakest attractions between molecules. So we have dipole interactions and dispersion forces. Dipole interactions happen when you have a polar molecule where the slight charge, like the slightly positive of one, will connect with the slightly negative of another. And I have a picture, okay? And then dispersion is the weakest of all because it happens between nonpolar molecules that rearrange for just a second into a polar molecule, but it doesn't like to be like that, so then it goes back away. So dispersion is the weakest because it's not natural, okay? So to see our pictures, after everybody write everything out, dipole interactions are on the left, where these are interactions between HCl. So if I drew the Lewis structure, hydrogen has 1 dot and chlorine has 7. So then if I connect them, then I get this molecule here. But that's a polar molecule because the chlorine has all the electrons and the hydrogen doesn't. So then we could say that the hydrogen is the slightly positive side because it doesn't have electrons, and the chlorine is the slightly negative side. Okay, so in this picture, which is gray on your paper, and I'm sorry, the orange squiggly lines are the dipole-dipole interactions that are holding the HCl molecules together. So if you notice, the chlorine of 1 will create this dipole-dipole interaction with a hydrogen of another. So that's what's happening here, is we have multiple HCl molecules that are being stuck together somehow. So dipole-dipole happens when you have slight charges, when it's polar molecules, and yeah, that's basically it, okay? The London dispersion, it's called dispersion because what happens are the electrons move. So normally, this II is a diatomic molecule, one of the Hawk fibers, okay? And each I has 7 dots. So if I had my 2 I's, and then I connected them together, that would be a very unpolar molecule, non-polar molecule, because everything is evenly distributed, everything's nice and neat, okay? What happens to make the dispersion is the electrons will move from one side to the other. So we could, and I don't know how many move and how many don't move, but let's just say that 2 out of these pairs on the left eye move over. So then now what it looks like is there's 1 pair left over on the left side, and then we now have 5 pairs, 3, 4, 5, left or on the right side. So because of that uneven distribution, it creates a polar molecule. So then we'd have this slightly positive, slightly negative, which would then be able to create that interaction between multiple, okay? But this doesn't normally like to happen because it likes to be nice and symmetrical, it likes to be even. So it's very weak in the fact that it wants to go back to how it originally was, so this bond will break, creating and letting it go back to its original form, okay? So dipole-dipole, when you have a polar molecule, look for the slight charges in the picture. London dispersion, you have to think about what was it originally, and when it was originally drawn, is it polar or non-polar? And if it's non-polar, chances are it's dispersion. Okay? So those are 2 out of our 3 types of intermolecular forces. The third type is called hydrogen bonding. Hydrogen bonding is the easiest to spot because if you have hydrogens in the compound, then it's hydrogen bonding. It's very, very similar to to dipole-dipole, where because hydrogen only has 1 dot, It's very low, has a very low electronegativity, so it will bond with other things with lots of electrons. Okay? So hydrogen bonding, the most important thing you need to know, because it's the easiest to spot, is hydrogen bonding always involves hydrogen. So when you're looking at a picture and there is hydrogen there, then you are talking about hydrogen bonding. So really, if I go back quickly, which I have a different picture for us to talk about hydrogen bonding, but the dipole-dipole interaction, there's hydrogen in that. So yes, it's dipole-dipole, but it's also hydrogen bonding. So that can be labeled as 2. Okay? But for the most common hydrogen bonds, we see with water. Okay? So let me get a new slide so that I can draw this better for you. Okay, so bear with me. If we had a water molecule, and we've drawn this Lewis structure a million times, not really, but it seems like it sometimes, where with a water molecule, oxygen has 4 electrons left, and then the 2 hydrogens connected. Okay? This is a polar molecule because the oxygen has the unshared pairs. Okay? So we could label this dipole-dipole if we wanted to, when we're done. For hydrogen bonding, we have to know slightly positive, slightly negative charges. So which part of the molecule is going to be the slightly positive part? The hydrogens, because the hydrogens have less electrons around them, and the oxygen has more. Okay. I wish I had a different color. Okay, so what will happen for hydrogen bonding is the hydrogen will connect with the oxygen, like that. But we could also, so in the other one, we just had like just one molecule connecting with one molecule. But I could also go like that. I could also go like that. Where it just gets very complicated because you can create all of these hydrogen bonds where multiple connections can happen. And that's why water is so unique, because it can have all of those connections happening all at once. Okay? So there we go. Do we have one more thing on the slide? Yeah, we do. Are we all go over this? Any questions about this picture? Yeah. Yeah. Like go like that? Is that what you're talking about? Like go to its own oxygen? Oh yeah, it could. I just didn't draw that because I thought it was going to get confusing. But yeah, that it could happen. Yeah, and that's what the water picture I showed before. There's all those connections happening, and so yeah, that's possible. Okay, the last thing in the notes is basically just telling you the reason why we have a very diverse different types of molecular compounds, and their properties are all very different, is because of our intermolecular attractions. These intermolecular forces are what make the properties different for everything. Okay? So